Hello, we're going to now try and put the capstone on all of the last 5 videos that we made. Probably it's more correct to say the last 4 because we will still need to know what the integral of secant is, so we did that in the first of the last 5 videos. But for supposing for n being, for n being a positive integer, greater than or equal to 2, we want to develop a formula for the integral of secant raised to the nth power. Okay, so a way to go about solving this problem, and by the way, this is also known as a reduction formula. For secant to the nth power. Okay. All right. So a way to go about getting a solution to this is to break down secant into secant n minus 2 power times secant squared d theta. And now you can see why I'm doing this. There's 2 reasons. One is because I want to use the integration by parts approach. Okay, so IBPS once again says that the integral of u times dv is equal to u times v minus the integral of v times du. Once again, I'll just mention that we produced a video where we derive this formula and we show how to use this formula on a specific example. Of course, here's yet another example that we'll be doing. And the second reason why I do that is because in my first video and in even the second video of this series of integrals of powers of secant, we there showed that when you take the derivative of the tangent of theta, and this is one that I asked us to just commit to memory, you get secant squared theta. Okay, so that's where this little piece is coming from, and that's why I write my original power of secant, namely secant to the nth power. I write it as the product of secant to the n minus 2 times secant squared, in anticipation of my having to use this result here. Okay. All right, so let's go ahead and now we're going to now put in what u and dv are. So u, we will let u be the first part, secant of theta raised to the n minus 2 power. Now I'm writing it in this way because I'm going to differentiate that, and when I differentiate that, I'm going to bring down this power, knock it down by 1, and then I have to use the chain rule to take the derivative of what's inside. So let's go ahead and do that. Therefore, du is equal to n minus 2 times secant of theta, and now I knock it down by a power, so I get n minus 3 times, I use the chain rule here, so it's going to be the derivative of what's inside here. And this is the other thing that I asked us to remember, is that the derivative of secant theta is secant theta times tangent theta, and then we have the d theta. Right, and so now I'm going to do the dv part. So the dv, so okay, if you didn't follow what I was doing here, let's just do a little recap. I'm letting this part be the u. Okay, this is the u, which goes right over there. So the balance of what's left over is the dv portion, which is this portion. Okay, so So if the dv is the secant squared theta d theta, then integrating that, we now know that the antiderivative of secant squared is going to be the tangent, right? So we see that this is tangent of theta. Alright, so now it's just a matter of applying this, so we now go ahead and do the IBPS here. And when I do the IBPS, I find that this is equal to u times v, so it's going to be the product of these two terms. Okay, so u times v is secant theta to the n minus 2 times tangent of theta minus the integral of v times du. So v times du is going to be the product of these two terms. So it's going to be v is tangent of theta, right, times all of this other stuff. So it's going to be times n minus 2 times secant of theta to the n minus 3 times secant of theta times tan of theta d theta. Okay? So now we would like to say, okay, let's keep going, let's clean this up a little bit, so we get secant of n minus 2 power theta times tangent of theta minus, I have a tangent multiplying with a tangent, that's going to give me a tangent squared, okay, and I have here a secant theta to the n minus 3 power times a secant to the first power. So if you add those exponents, n minus 3 plus 1 is going to be n minus 2. So I get that this is the minus the integral of tangent squared theta times, and by the way, before I do that, let me pull out this constant n minus 2. So it'll be minus times the quantity n minus 2 times the integral tangent squared theta times secant n minus 2 theta d theta. Okay? Alright, and what does that mean? Well, now we have to invoke the I Trig identity. So this is another one of those that, if you've been following these videos, we showed how to get this trig identity, namely that tangent squared theta plus 1 is equal to secant squared theta. That is to say that tangent squared theta is secant squared theta minus 1. And I'm going to put that result in for this term here. And so when I do that, I find that this is equal to secant n minus 2 theta times tangent theta minus the quantity n minus 2 times the integral of secant squared theta minus 1 times secant to the n minus 2 theta d theta, and then that is equal to, we'll distribute this, so I get secant to the n minus 2 theta times tangent of theta minus the quantity n minus 2 times the integral secant squared times secant to the n minus 2 power theta. That's going to be, we add the exponents once again, we get secant n minus 2 plus 2, so it's going to be secant n to the nth power, so it's going to be minus the quantity n minus 2 times the integral of secant to the nth power theta d theta. And then I get a minus times a minus, so that's going to be a plus n minus 2, that quantity, times the integral of this, what's left over, secant to the n minus 2 theta d theta. And once again, and we've shown this in previous videos, we see here, in fact, we see this integral right here, which is what we were actually after. And so when I take this entire quantity over to the left-hand side, when I move it over, I'm going to get, we had one of those. Now I'm going to add n minus 2 to the one that I had, so I'm going to have 1 plus the n minus 2 of the integral of secant of raised to the nth power theta d theta, okay, is equal to what's left over. So we get secant to the n minus 2 theta tan theta plus n minus 2 integral of secant raised to the n minus 2 power theta d theta. Okay, and now what's left is to see that in fact what's in the square brackets here is n minus 2 plus 1, so that's n minus 1. Okay, so this is all n minus 1. And so if I were to divide both sides by that, I get the result that I was looking for. So divide both sides by n minus the quantity n minus 1, and so we find that the integral of secant to the nth power theta d theta is equal to secant to the n minus 2 power theta times tangent of theta divided by the quantity n minus 1 plus the quantity n minus 2 divided by the quantity n minus 1 times the integral of secant to the n minus 2 power theta d theta, where n is a positive integer greater than or equal to 2. Okay, that is to say n is greater than or equal to 2. Alright, so now let's just take a quick look at this in light of some of the things that we had shown in the last several videos. So for example, I'm going to do an example or two here. So let me draw a line here. So for example, suppose that n is identically 2. Okay, if n is identically 2, then let's go ahead and apply this here. So I'm going to find that the integral of secant squared theta d theta, just plugging in, it's going to be secant to the 2 minus 2 power theta times tangent of theta over 2 minus 1 plus 2 minus 2 over 2 minus 1 times secant to the 2 minus 2 power theta d theta. And we see that secant to the 2 minus 2 power is just to the 0th power. That means that secant to the 0th power is just 1. We get tangent of theta divided by 1 on the denominator. And notice over here that I get 2 minus 2, and so this is just going to wipe everything else out. So it's exactly what I expected it to be, namely that the integral of secant squared theta d theta is in fact just tangent of theta. And of course we have a constant of integration when I do that. And that's exactly what we had shown previously. And you can do this for any power of n. We already showed in the several past videos n being, of course we started with when it's just secant, and this formula doesn't apply when n is 1. We're saying it's a positive integer greater than or equal to 2, but we've shown it for the integral of secant, and then all the powers 2, 3, 4, and 5 in the last 4 videos, and now we have a generalization of that, which is known as your reduction formula. Okay, hope this was helpful to you. Hope you were able to follow it, and we will look forward to seeing you in a future video.